Okay, thank you. First of all, let me thank the organizers for giving me the opportunity to present my work. That was done with Jan Louis, Danny Martinez-Pedera, Roberto Volando, and Alexander Westphal. And I want to talk about this general method of Kahler uplifting, one part, and the other part I will present an example where we realize the Sitter vacuum using this method. So I think I can be brief on the introduction. We want the Sitter vacuum because we observed that the universe is accelerating on large scales, and the simplest explanation for that is the Sitter vacuum with a small cosmological constant. And the setup I'll be using in the following is this, I guess by now, classical things. So non-perturbative effects in the superpotential, leading alpha prime correction to the Kahler potential, and quantized fluxes. And so starting with a variety of ways to stabilize the moduli, there's different ways to uplift, and there's three branches, so to say, of moduli stabilized scenarios in 2B. The oldest famous one is the KKLT scenario, where the superpotential has to be tuned small and alpha prime corrections can be neglected. Then there is this branch where the alpha prime corrections are important, and then you can either go to very large volumes, realizing the large volume scenario, or you can go to not so large volumes using W0 in this window, and then you have the method of Kahler uplifting, which directly realizes the Sitter vacuum from the F terms. And here you first end up in an anti-de Sitter vacuum, and then there's various ways to uplift. For example, anti-D3 branes, F terms from matter field, F terms from gauge theories, and in the large volume scenario you can also use D terms, which are not available in KKLT because the F terms are 0, so D terms are also 0. And very recently, this nice effect this is also an F term effect from dilaton dependent, and I will focus on this scenario because it most well suits our purposes, which is that we want to make a model-independent analysis as possible, what the conditions are to find the Sitter vacuum in 2B supergravity. And also, if we want to construct an explicit example, it's nice to have everything available already in the F-term potential and not having to add additional sectors. Also, it's manifestly supersymmetric, which are some of the others also. But this is the motivation to use this setup. Okay, so I get this is the Kahler uplifting scenario. So you can just look at the scalar potential for certain manifolds, a Swiss cheese type, and then in a certain limit, you can expand the scalar potential and treat it analytically. So this is this alpha prime correction has to be small, but it's not as small as in the large volumes case. It's a different branch. Non-perturbative effects are small compared to the flux superpotential, and you supersymmetrically stabilize the dilaton and complex structure moduli to zeroth order. And then for the I think Joske also showed this already. For one modulus, you can make a very simple form of the scalar potential, which is just two terms basically, and your condition for the sitter is just given by this constant c. So it tells you what parameters you have to realize in order to go from an ADS to the sitter and eventually becomes a runaway. This has to also be fulfilled, but in the scenarios where the volume is large, there's the potential of the complex structure moduli is positive semi-definite up to a correction of this psi over V. So this is generically fulfilled. And one feature that one has to keep in mind in this Kahler uplifting scenario is that the overall volume depends on this gamma S intersection and then the gauge group rank of this first T1 cycle. So if you want, you will never end up with an exponential volume, but if you want to end up with a large volume, you typically need to realize large gauge group ranks. So one question is how Yes. So the question is how natural is that, or how can that be obtained in general in Calabi-Yau manifolds? And what we just did is we analyzed this mini landscape, which is given by complex projective hypersurface in complex projective spaces. So it's a weight system given by 5 weights, and we only focus on those where the last weight is the sum of the other ones. This is then directly in an uplift form for F-theory, and you know what the orientifold coordinate will be with this psi. And so typically, if these ones are bigger than 1, then you will have to add additional resolution weights, and you will end up with more Kahler moduli. And the Calabi-Yau is given as a hypersurface of this, the orientifold squared equals 0, which is then a polynomial of degree 2n psi, or these dots indicate the degrees from the resolution weights. And how do you know how many branes you can put? This is given by the D7 tadpole, so the class of the D7 has to be cancelled by the class of the O7, which is then given as this weight. Or in more detail, the D7 equation is given by this form, where this eta and xi are sections in the canonical bundle and the canonical bundle of the base. And so this one with one brane that cancels the tadpole, but you can also factorize this equation. So just factorizing corresponds to realizing an SP group. But then you need to fulfill the constraints that in order for the brane to be holomorphic, that these degrees here have to be positive. And you see that the most restrictive comes from this first coordinate. Yeah? So this, in order for this to be greater than 0, n1 always have to be smaller than 3 times n psi over n1. And then what we did is we just scanned through this Kreutzer-Skarke database for this number. So very simple. And then you see what you can end up, what kind of gauge group rank you can end up with. So this is what you would expect. If you go up with H11, then also your gauge group rank gets very big, potentially gets very big. It's still, you enforce this factorization, but you have the opportunity to do this. And yeah, so you see that this critical gauge group rank is even for, let's say, 10 Kahler moduli, you usually have enough gauge group rank to potentially end up in the volume of, say, 10 to the 3, 10 to the 4, something. Okay, so this is a general motivation to look. So I will in the following look at one example, which is actually this point here, yeah? Just below the line, which we will analyze in detail and stabilize the Kahler moduli and complex structure moduli, and see that this ends up in a de Sitter vacuum. So, of course, if you want to realize a fully consistent model, this is more complicated than just doing the scan. So there's various things you have to check. So you need this non-perturbative effect to stabilize the Kahler moduli, and then the cycle has to be rigid, or it can be rigidified by gauge flux. The manifold has to be Swiss cheese. You have to cancel Fried-Witten anomalies. You have to you might be forced by factorizing this brane equation to have also large gauge group ranks on other divisors, which might screw you up your large volume in the end. Your Kahler moduli have to stabilize inside the Kahler cone. You have intersections from the various brane stacks that might also, again, yield your superpotential contribution 0. You have to fulfill the D3 tadpole. And finally, your complex structure moduli have to stabilize in such a way that W0 and the VEF of S, so the string coupling, have to be in a right interval to allow you the uplifting. So these are the things you have to fulfill. And a very much famous example that has been studied a lot in literature before is this CP11169. And our kind of prototype was this Denef Douglas Fourier construction, where they constructed an ADS vacuum, and we want to construct a de Sitter vacuum on this manifold. So this is the 11169 is the original weight system, and if you resolve the singularities, then you end up one more line and end up with 2 Kahler moduli, 272 complex structure moduli. And the divisors we want to use to stabilize is D1 and D5, which are these Hodge numbers. So you see that D5 fulfills a sufficient condition to carry a non-perturbative contribution because these two are 0, this is 1. D1 doesn't, but we can use gauge flux to turn this down to 0, so effectively make this divisor rigid. We can show this explicit. The volume is of this form. So in this basis of D1 and D5, it's not Swiss cheese, but in some sense, this is just a correction. And if you do the numeric, our analytic treatment doesn't work anymore, but if you do it numerically, you still find that it works to find this de Sitter vacuum. And the really nice thing about this manifold is that even though the complex structure modular space is so large, there's a mirror construction long ago that allows you to construct the prepotential and including instanton effect, so you know all the formulas for W and Kahler potential from the complex structure modular side, which is usually not the case. Yeah. So this is why this is a nice example to study. And then, so this is our model that we realize. So maximum gauge group rank is 27, but for technical reasons we only realize 24. This forces you to have an SO24 on D5. D5 is rigid, so this carries a non-perturbative superpotential. D1, as I said, can be rigidified, which breaks the SP to SU. And then there's the intersections of D1 and D5. But you can switch on gauge flux that cancels the Fried-Witten anomalies in such a way that the net flux is trivial, so there's no chiral matter or D terms that again screw up your superpotential. So this is a thing that works out if you do this for this model. How generic that is maybe the question. So, but for this model it works. You can calculate the D3 tadpole is this value. So in the end you end up with this superpotential for the Kahler moduli stabilization. And then you look at the scalar potential, find the extrema, and you find that they are stable at these VEFs. So the force cycles are also large enough. The volume is 52. And the parameters you put in by hand are these. So A and B also depend on the complex structure moduli. Just nobody knows how to calculate them. And what we want to do in the remainder is realize this W0 and this S explicitly on the complex structure side. So there's also one comment about this. So you might think you just fix the 2 complex structure moduli, but effectively you fix all of them, because again this will be an extremum and the potential is positive definite up to corrections. And so yeah, this is the mechanism to do this. You first solve this equation for the flux quanta. So you have 2 complex structure moduli, so you have 6 3 cycles in a symplectic basis, and then you insert the instanton corrections, and this generates you a non-zero shift in W0. Here it was 0, and you can just see if you get something that's useful for the Kahler moduli stabilization. And one solution that we found here is this flux vector. The tadpole is, remember, it was 114, so this is less. You can fill up the rest with gauge flux or D3 branes, and the moduli are stabilized at this value. W0 is this. So it also, so we've tuned here. You see we've kept B to 1, and we've tuned A from 1 to 1.11. Yeah. So this is the by hand value that we set. Everything else comes out of the analysis, and it's a posteriori justified because you really see that there's a mass splitting. So the Kahler moduli are at least 2 orders of magnitude smaller than the dilatonian complex structure moduli. So it makes sense to set this A to a constant of the same order of magnitude as.
What are the units there?
Planck units. Okay, let me come to my conclusion. So we have found a sufficient condition to stabilize moduli in the de Sitter vacuum. to B. And SUSY is only broken by F terms, well controlled, and large gauge groups can be realized for many Kahler moduli. And if you really want to construct an explicit example, there's a lot more work to do. But so we did this for this example and could really do everything explicit except for the dependence of the one-leaf determinant on the complex structure moduli. And what one could do now is, for this manifold, to consider how many solutions do I get that are in the complex structure sector that allow me the sitter. So I could do the statistics of the sitter by actually constructing the solutions. And I mean, I think so far most statements in the literature are about anti-de Sitter vacua and KKT, and then it's not so clear what happens once you uplift. Okay, thank you.
Okay, so we have time for, let's say, one question for Markus. Well, Christoph, Markus, do you want to do it separately?
Do you have to take into account the back reaction of gauge fluxes?
What do you mean by catch?
It contributes to energy.
Yeah, I mean, yeah, we do not look at the D7 moduli.
But it does contribute to vacuum energy.
Yes. So yeah, we have not considered it. Yeah.
Is the surface motor broken by gauge condensation?
Yeah.
So this is a very small scale. So is it for the explaining current acceleration?
Yeah, I mean, this is the goal, to find to explain the current acceleration of the universe. Yeah. And the Gaussian condensation. I mean, they are small, but because of this no-scale structure, they are the first non-zero effect.
All right. So may I suggest that